Hello everyone, in this video we will be solving an interesting problem 322 coin change. We are given an integer array coins representing the coins of different denominations and an integer amount. We need to return the fewest number of coins that we can use to make up that amount. If the amount cannot be made, then we need to return -1 as the output. In example number 1, we have 1, 2 and 5 coins available and the amount is 11. With infinite supply of these three coins, we need at least 3 coins, 2 5s and 1 1 to meet the total 11. While in example number 2, it is not possible to get the amount 3 with only one coin valuing 2, hence the output is -1. The problem statement is very easy to understand, but the optimal solution is slightly tricky. So let's switch to whiteboard and discuss the solution starting with the brute force approach and then following up with the optimized one. The simplest way to solve this problem is to use backtracking plus greedy algorithm, where we'll try to identify all possible combinations between the three coins that are given to us in the input to see if we can add them up in different pairs to get the total amount that we are looking for. Using greedy algorithm will also serve the purpose because we are looking for the minimum number of coins that can add up to the total. In backtracking, we'll try to build a decision tree with 11 as the parent node, and we'll try to use all of the coins that are given to us to see which one can give us the best possible results, that is the minimum coin. In this example, we have 3 coins in the input, so we have 3 decisions that we can take, 1, 2 and 5. Depending on which coin we use, the remaining amount will be different. If we use coin 1, it will be 10, with coin 2, the 9, and coin 5 will be 6. We repeat the same cycle for each of the nodes where we can use 1, 2 or 5 coins to lower the remaining amount to 0. We will continue this top-down approach to build the decision tree until each of the leg reaches 0 or negative. During the traversal, we will be recording the total coins that we used for each leg, which will be used to calculate the minimum coins once amount reaches 0. Let's say if we do not find any combination that can lead up to the amount that we are looking for, the output will be -1. Because we are trying to build all possible combinations to get the minimum number of coins, the total time complexity of this solution is going to be O of n square, where n is the number of coins given to us and the space complexity is going to be O of 1. As we are only using a couple of variables to record the minimum coin and the total coin for each leg. I hope this explanation was helpful in understanding how we can use the backtracking and greedy algorithm to solve the problem. Let me highlight some of the inefficiencies in this approach before we discuss the optimized solution. If we try to build the decision tree with node 10 as the parent node, we will get 9, 8 and 5. Node 9 is duplicate because it is already part of a different leg. So repeating the same calculation causes the solution to be inefficient. There will be several more nodes which are duplicate if we try to build the entire decision tree. Now let's try to solve this problem using a different approach. As we are trying to avoid doing repeated or duplicate calculation, the best solution to use here is dynamic programming using memoization, where we'll use an array to store the minimum amount of coins needed to reach that amount. So instead of repeating the same calculation again, we can just do a lookup in the dynamic programming array to see what were the minimum coins needed for that amount. The earlier approach that we discussed using backtracking was a top-down approach where we started with the total amount and trying to reduce it to 0. But now we'll use the bottom-up approach where we'll start with solving the amount as 0 all the way to 11. Let's do a small dry run which will help you understand this concept better. As the amount in this example is 11, we'll use a dynamic programming array of size 11 plus 1, that is 12. If we keep the size as 11, then the last index will be 10, so we won't be able to calculate the value for 11, which is what we are looking for. It will make more sense as we proceed with this approach. As we are planning to use this dynamic programming array to store the minimum number of coins, we need to pre-fill with some value other than 0. If the lowest denomination of coin is 1, the maximum amount of coin that we will require is going to be the same amount, which is 11. So we can default the values for all of these entries to 12 and I will use this value at the end to determine if I was able to find a valid combination of coins to meet the amount. Now let's start the iteration with I is equal to 0. We will be using the value of I as the amount that we are trying to build using the coins available. If the amount that we are seeking is 0, we technically don't need any coins to meet that criteria. So we'll just update or replace the value in the array to 0 and increment the pointer. With I is equals to 1, we need to determine how many minimum number of coins we need to reach this sum. As we have 3 coins available in the array, we need to try 3 combinations. Let's say if we use coin 1, the remaining amount will be 0. Now we need to look up the 0, what was the minimum number of coins needed to reach that sum in the dynamic programming array. As we have already calculated the minimum coins to reach to sum 0, we don't need to repeat it again. So we'll just take that value, increment it by 1 because we are using a new coin with value 1 and save it as a minimum in the DP array at I is equal to 1. We tried the combination with coin value 1. Now we need to repeat it for coin 2 and coin 5. Because the value of coin 2 and 5 is greater than I, which is the sum, we can't use it. If we use it, the total will be negative. So we'll skip the calculation and increment our I to 2. With I is equals to 2, you again have 3 combinations we need to try with coin 1, 2 and 5. Starting with the first coin of value 1, the remaining will be 1. Now we need to do the lookup in the DP array. For index 1, the value in the array is 1, which means I need a minimum of 1 coin to meet 1. So with that 1 in the DP array and the new coin that I am using, the total will be 2. As this value is smaller than the current value in the DP array, we can override it. I hope you are able to follow how we reuse the calculation we did for I is equals to 1 and we are doing the calculation for 2. Now we'll repeat the same process for the next coin, that is 2. After taking coin 2, the remaining amount is 0, and if we do the lookup in the DP array, the corresponding value at I is equal to 0 is 0. So the total coin needed here will be 0 plus 1, which is 1. And for the last coin, that is 5, as the value is greater than I, we don't need to do any calculation, we can just skip it. So between the calculation that we have done, the smallest or the minimum number of coin is 1, so we'll save that in the DP array and continue with the run. With I is equals to 3, we again have to make the decision starting with the first using coin number 1. The remaining value will be 2. Doing the lookup in the array, the value is 1. So including the new coin that we are using, the total will be 2, which is smaller so far. So we'll just save that in the array. The next coin is 2. If we use it, the remaining amount will be 1. Doing the lookup for 1 in the array, the value is 1. So using that 1 plus 1, the total will be 2. As it is same as the previous calculation that we did, it does not matter which one we'll use. So we can simply save 2 in the DP array for I is equals to 3. We continue to iterate through all of the elements in the dynamic programming array until the end. And once we reach to the last element in the array and complete the calculation, the value that we save at index 11 will be our output.
As you must have noticed, in this approach, we are not duplicating the calculation. We are instead building on top of the past calculation that we have made.
With this solution, our time complexity is O of m into n, where m is the amount that is given to us and n is the total number of coins in the array. This is because we are trying to pair each value of I with all of the coins available to us so that we can calculate the minimum number of coins we can use. While the space complexity is O of m, as we are using the dynamic programming array to store the minimum number of coins needed for each value of I. I hope you were able to understand the explanation. Let me show you how we can implement this using Python. In this Python solution, I start by adding a couple of validations to make sure that the coins array is not null and the length is greater than 0. If either of the conditions are not met, then we return 0 as the output. After that, I am initializing a new array dp and setting the size to amount plus 1 and pre-filling it with amount plus 1 as the default value. For the first value in the dynamic programming array, I am resetting the value to 0 because for sum 0, we don't need any coins. After that, I'm starting a for loop to iterate through all of the elements in the dynamic programming array. And inside the for loop, I'm iterating through all of the coins so that we can try all possible combinations. If coins value is greater than I, we cannot use it because the difference between the two will be negative. Hence, I'm adding a check inside the for condition to make sure this do not happen. If the condition is sufficed, I'm using the min operation between the current value saved in the dynamic programming array against the remaining amount after we use the value of the coin. And whichever is the smaller value is going to be saved back into the dynamic programming array at the corresponding index. After the for loop is complete, I am checking if the dp.amount, that is the last element, is it still equal to the default value. If yes, it means we were not able to find a valid combination to reach to the amount, so we return -1 as the output, or else return the corresponding value saved in the dynamic programming array. This code, when submitted on LeetCode, beats nearly 91% of the submissions in terms of runtime and 43% in terms of memory. Thank you for watching this video. I hope you were able to understand the explanation. The details to access the source code is available in the description below. Feel free to check that out, and I will see you in the next one. Thank you.